And then I have to get to set. Let's see my
So,
yeah, and the camera's doing something. Okay, so good. Let me just get on here to make sure I can see you.
Talk about so you get to talk about
So today we have William Dugan from UMass Amherst visiting us.
I'm doing one thing.
He'll be talking about cases of generalized Pitman-Stanley.
All right, thank you so much for that introduction. I'm thrilled to be here. I honestly can't thank you all enough. Thank you, Professor Yip, for hosting me today and for great lunch. And thank you, just organizers, for again like rescheduling me. I was supposed to be here a few weeks ago when I was sick. But yeah, I have this talk to tell you about. It's been something I've had a lot of fun with, and I hope you enjoy hearing about it. Yeah, it's an honor to be here. So this is joint work with my thesis advisor, Alejandro Morales, as well as Annie Raymond, both at UMass Amherst. And then Maura Hegarty was our research undergraduate a few summers ago, who's now a graduate student at MIT. So as an overview, I'll start by telling a little bit of background. So I think this room knows a lot more about polytopes than I certainly do. So I'll go through background pretty quickly, but I'll tell you a little bit about flow polytopes just in case anyone in the room, and then generalized Pitman-Stanley polytopes. Then we'll get into the results. We have two different papers in the works, one on volumes of Pitman-Stanley polytopes, the other on vertices and faces. The talk you're seeing today will only be about vertices and faces. The volume will have to wait until next year, but I'll have a teaser slide at the end. All right, so to begin, I will tell you about flow polytopes. I should maybe give one more preface, which is to say is I'm a tiny bit tired today, so if I kind of like blank on my slides for a second, I apologize in advance. I've actually practiced like a dozen times, so I do know what I mean to say. Just if I forget for a second. All right, so to start, let's lay some conventions. All polytopes in the talk are going to be integral. And due to exposition, like sometimes I don't want the graphs to be too cluttered, so I will sometimes remove edge labels. But all graphs in this talk are directed. Edge directions can be assumed to be from left to right and top to bottom. So, for example, this graph at the left is actually representing this graph at the right. Yeah. So flow polytopes. So what do you need to define a flow polytope? We need two pieces of data. The first is going to be a directed acyclic graph. We will be using the standard vertex set of n+1. So vertices will just be labeled 1 up to n+1. And then the second piece of data that you need is a net flow vector. So this is a vector of integer numbers for which we have n degrees of freedom. So we choose the first a1 up through an, and then the last vector, or the last element of the vector, will just be the negative sum of the previous ai. We call this the net flow vector. And I should maybe quickly say, I noticed on the computer it says the microphone isn't working properly. Is that
I think that's okay. Yeah, I mean, I'm checking things, so I think it's okay. It gets it from here, not there.
I see.
Otherwise, you could be a silent movie.
Oh yeah, that's true. And then maybe we can have like some like voiceover.
Yeah.
But we can
What
just.
I don't understand is, yeah, see, you don't have your slides over here. So this is actually what I'm seeing now. So your slides here are not over here.
Oh, I
This
see.
is what's being shared. So maybe I should get you on this meeting. Can I do that?
Yeah.
If you wanted, I'm sorry to interrupt this.
Oh, no
Can we have a
Is
small intermission of about 90 seconds? Okay, so let's see if I can mail this to you. You would have to get onto Zoom.
Maybe I should. And you'll be sending me in.
Yeah, I guess I'll send you an email. It'll be easiest.
Maybe have a meeting number. You also just Oh,
Yeah, so let me give you the meeting number. I hope I remember the password. It's 841. 841 5900 1077. And just say join. Shoot. Now I have to remember my passcode. Oh, I'm so sorry.
Oh, no.
I think it's, oh, meow, MEOW.
Should be discreet now.
Well, that's more letters, so, okay, so you should be able to join. And, let me see. Okay, so I definitely see you. And then,
Now I share my screen.
Yep.
And I'll keep my computer muted.
yeah,
Disable share.
yeah, so for some reason, I'm still,
Oh, you have to let him.
you know what I'm gonna do? Just do your thing. I'm gonna move this camera and like move from between here and
Yeah,
here. I'm gonna be
that sounds
old
great.
fashioned. I'm gonna be like, Hollywood, which I'm not. Okay. Okay, go ahead. I'm sorry.
So I'll just, I guess I'll leave this meeting.
Yeah, just, it's fine. Just keep going. Cause, okay, yeah.
Yeah.
All right. Good to see you there.
Thanks so much. So should I resume?
Yeah, keep on going. Fine, I'm sorry.
No, thank you. So yeah, we need two pieces of data. The first is this directed acyclic graph, and the other is the flow vector. And then with these two pieces of information, we produce a flow polytope, which would denote math cal f g a. And this is the set of, as a set, it's the set of flows, which are functions from the edge set to the non-negative real numbers, such that the net flow at vertex I is AI. So that's a very brief description, but let's maybe kind of do definition by example. I realize it's kind of probably small for people to factor in. But yeah, so the idea here is on the left, we have a directed acyclic graph in red, which is not very super visible, but we have some net flow vector, 1, 0, -1. And for example, the way Alejandro kind of would tell me about this kind of thing is that you kind of think about water kind of flowing through a network of pipes. So we think of the directed graph as kind of a network of pipes. The net flow vector on the vertices is kind of representing like kind of water units of flow, like entering or exiting. So entering if it's positive, exiting if it's negative. And then the edge labels are kind of, or edge values are kind of amounts of water through the pipes such that at every junction, the vertices, the flow is constant. And so what we have here, so in general, our flow polytope will be of dimension E, like cardinality E. This will be live in dimension, sorry, the ambient space, I mean, will be R to the E. So this is in R4. But we can see that, for example, any value we place on this top edge right here, say call it X, then for flow to be conserved at the first vertex, the other edge has to be 1 minus X. And similar argument for the second set of parallel edges. And so in fact, really our polytope only has 2 degrees of freedom, 2-dimensional polytope, which is the square. And so some point in this polytope, like after you project onto the first 2 coordinates. So some point in this polytope is represented by x, y from these from the edge labels to the. Okay, probably over-explained that. Here, without further ado, is another example. This is K4, the complete graph of 4 vertices, and all edges are directed left, right? And so, for example, at this first vertex, now we have just an arbitrary net flow vector, A1, A2, A3. And at this first vertex, we have 4 variables leaving, x14, x13, and x12. And so the sum of those must equal the net flow at that vertex, A1. And similarly, x24, x23 are leaving the second vertex, and x12 is entering. So we have the sum of x2, x3 plus x2, x4 minus x1, x2, because they have different directions, must equal a2, and so on. And so we'll get 3 hyperplanes, which kind of cut out our polytope in 6-dimensional space. All right. So without further ado, let me then tell you about the central object of this talk, which is the generalized Pitman-Stanley polytopes. So let's first start with the original Pitman-Stanley polytope, which I'm sure many people are already familiar with. So starting with some integer, not a natural number vector, the Pitman-Stanley polytope is defined as follows. And maybe the symbols like kind of confusing at first, or like kind of a lot of symbols at first, but we can unpack it. In particular, what's going on? So we have the first condition is saying that we're living in the positive orbit because all the variables are non-negative. And the second condition is saying that you're looking at vectors x and r to the n that are less than your vector a in dominance order. And what is dominance order? So it's just exactly what I've written here. The partial sums for every I are less than the partial sums for every I. And this is a figure I really wanted to make this bigger last night when I realized how small this is going to be. But basically, you can see like we're living in the positive orthant, and then this is saying x1 is less than or equal to 1. So here is the Pitman-Stanley polytope at 1, 1. And so then we have x1 plus x2 is less than or equal to 1 plus 1, which is 2. We're getting this second line. So a bit of history on these polytopes. So Pitman and Stanley originally defined these polytopes in the for the notion of in the context of empirical distributions from statistics. In particular, they showed that it is combinatorial equivalent to a product of simplices, depending on which entries of A are non-negative. I'm not going to dwell on that, but if people want to see later, I can show you the biject. The description is very simple. And in particular, because it only depends on which entries are non-negative, if all the entries of A are non-negative, you have a product of 2 simplices over and over again, which gives you the hypercube. So in fact, you can see on the previous slides, it is combinatorially equivalent to a 2-cube square. And then you might have heard about them for other reasons. If you study generalized Hermite-Hydra, this is one of the go-to examples. And also they're related to parking functions in the sense that their normalized volume, the normalized volume of the Pitman-Stanley polytope at all 1 is equal to n plus 1 to the n minus 1, which is the number of parking functions. And here's another example of one where you can see, again, it's not equivalent to a cube, but it's combinatorially equivalent because it's based on. All right, and so the launch point for the generalization comes from the result that the lattice points of the Pitman-Stanley polytope are in bijection with plane partitions of a certain shape in a certain kind of entries, namely 0 or 1. So quickly, what is a plane partition? A plane partition is a filling of a Young diagram such that all of the entries decrease from left to right and decrease from top to bottom. So for example, there are 5 plane partitions of this particular shape with entries 0 and 1. And then how are we getting the shape from our vector A? Or once again, having these partial sums. So like these partial sums kind of appear all over the place in this work. But now they're in reverse order. So for example, the first row of our plane partition will have A1 plus A2 plus da 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 plus AN entries. And then the last will just have A1 entries. So for example, this was our Pitman-Stanley polytope at 1, 1. And you can see that, the first row is 2 because 1 plus 1. And then the second row is just 1. So that's an example of connection to plane partition. So the next step in the history that was very relevant for us is a result of Baldoni and Verne in 2008, in which they showed that the Pitman-Stanley polytope is a flow polytope. Now, to be a flow polytope, as we discussed, you need to say what the graph is and what the net flow vector is. And I'm illustrating that here with this graph. So it's a modified path graph in the sense that you have like a path on n vertices and then one extra vertex, the sink. And the sink is connected basically to all of the vertices by one edge, except for the last vertex, which is connected by a double edge. And then whereas in the flow vector, well, you just put the A, that's from your Pitman-Stanley polytope, along the path. And then the correspondence between the two, the Pitman-Stanley polytope and the flow polytope, is just given by where I put the variable. So like variables along these, like kind of rightward edges, give you the bijection to a point in the Pitman-Stanley polytope.
And the flow among the edges in the path is determined by those x's.
Exactly. Yeah, thank you. So now I'm going to tell you about generalized Pitman-Stanley polytopes. And the name is a little bit strange because actually these are not due to us. These are actually due to Pitman and Stanley stuff. And the reason we call them generalized is because they're only kind of written as a remark in their paper. And so like if I were to tell you Pitman and Stanley polytope, you would think of, you know, this one, like the one corresponding to this graph. So we need to say generalized to indicate that like these are kind of new. Though there was some kind of like assembly that we did to make the full definition, but again, this is their definition. So they suggested that we could generalize the same construction to a polytope having lattice points in bijection with plane partitions, having entries instead of 0, 1, 0, 1 up through m for any m. So here's the rigorous definition. It's a lot to write down, but again, I can kind of unpack it by explaining what all this is. So we generalized, they generalized the Pitman-Stanley polytope in two ways, namely M and B. Before it was just N and A, now we have N, A, M, B. And the M gives us a sequence of vectors, rather a chain of vectors. And all of these vectors need to be less than or equal to each other in dominance order. The dominance order is this is kind of like the dominance order of polytope. So they're less than or equal to each other in dominance order. And there's M of them. And then at the far right, they're less than or equal to the vector A in dominance order. At the far left, they're greater than or equal to the vector B, the new vector B in dominance order. And so I said that these would be in bijection with certain plane partitions. So let me show you how these new parameters change the plane partition. So the M, as I alluded to, makes the entries instead of 0, 1. The entries are now 0, 1 up through M. But the new addition of the parameter B allows the shape of the plane partition to change as well. So instead of being straight shapes, as they were before, now they're skew shapes, where we take the shape determined by A, and then we take the shape determined by B in the same way and just subtract it off. So for example, if A was 2, 1 and B was 1, 0, then the shapes we would get would be 3, 1 minus 1, 0. And I really should have done a bigger M since the M equals 1 was the original case, but there were too many, so I couldn't fit them on the slide. I did M equals 1 for simplicity. But for example, if M were 2, then you could have entries with 2 as well. Yeah, and we noticed that this wasn't studied much in the literature after it first appeared. And it turns out that the structure is complicated and rich and kind of a treasure trove of cool problems and connections to other areas of combinatorics. So any questions about, that's kind of my full list of background. All right. Let's get on to the main result. So calling this a main observation, it's kind of like the one thing I would want you to take away from this talk if you only took away one thing. But I'm only calling it, so it is a theorem, but we're calling it an observation as far as the slides go, because once you kind of see this graph, the proof is there's nothing much to the proof. But the result is that this generalized Pitman-Stanley polytope is indeed integrally equivalent to a flow polytope. This is the analogous, an integrally equivalent means that preserves the integer lattice. So this is like the generalization of Baldwin-Burns results to this generalized. What is the graph and the net flow vector? Well, now we have the grid graph. So this is the grid graph for 3, 4, but in general it'll be NM. So there'll be N rows and M columns. We put the vector A along the leftmost column, the vector negative B along the rightmost column, and then zeros everywhere else except for the sink, which just is what it has to be to make it a flow vector. Yeah. And in the case that b equals 0, we kind of want to sanity check that we do get Baldwin-Burns result back. So we can show that it's integrally equivalent to a flow polytope over this graph, where kind of now there's only m edges, or m columns. So the m plus first column has kind of collapsed into these edges. And the reason this is great is because now when m is 1, we just get like kind of block off all of this. We just get this one column, which is exactly the path graph or modified path graph that holds on the right. So that was kind of one of the main takeaways. But from here, the project gets just even more exciting because we can use now the theory of flow polytopes to investigate the structure of this generalized Pitman-Stanley polytope. We have results for different combinations of A and B, some for all A and B, but for the purpose of the talk and exposition, I'm going to assume B is 0 for simplicity. Okay, so our first result in this direction of structure is we were able to find recurrences on the number of vertices and faces. And to do this, I want to talk about one particularly powerful theorem, which we're going to use over and over again. It's kind of an amalgamation of theorems, actually, from Pilla in 2003 and Gallo and Sedini in 1910. What it says is that if you want to study the faces of a flow polytope, it suffices instead to study the subgraphs of your underlying graph. So in particular, it's saying the d-dimensional faces of your flow polytope correspond to subgraphs of G, such that I actually left out on the slide, but you have to forget the directions of the edges. And then the first Betty number must be equal to D. And then the only other condition is this, which is that it's the support of an A valid flow. So I'll give an example, which I think makes this more clear. Let's see an example. So this is the same flow polytope we had before of the square. And now imagine I look at some subgraph here in red. So I'm just looking at this topward edge and this bottomward edge. And I can see that, well, that corresponds to a flow in which I put 1 for x and 0 for y. And I get a vertex 1, 0. And you'll notice the subgraph has Betty number 0. So it's the 0-dimensional face. And the reason it's Betty number 0, so especially because our graph is planar, all we have to do is look at cycles. So the Betty number is defined as edges minus vertices plus connected components, but it's also the dimension of the cycle space of the graph. So looking at another example, here's another tree. I get that by setting x equals 0 and y equals 1. And in general, all of the faces, so there's 9 faces total, and I can kind of superimpose them all in this way. So for example, there's 2 cycles, again, cycles after you forget directions and edges, for this full face, and that's how we get a 2-dimensional face for the polytope. So now counting faces becomes a matter of counting graphs. Oh, and then what did I mean by A valid? Well, I just meant that there are some subgraphs, such as this one, which is not actually a valid flow, because no matter how I assign, it's a subgraph, but like no matter how I assign values to these edges, it won't ever be a valid flow. So I kind of can't look at this subgraph.
Sorry. So if you have the 1, 0, minus 1, like suppose you have a unique source of time, is it enough that every edge is contained in a route? Like if you have a subgraph where every edge is contained in a route, then that does.
Yes, I believe so. Yeah, with a unique sink. Yeah. Yeah, great. Great question. Other questions? But yeah, I should say the amazing thing is too that these results with Hilla and Galantinis are they could also be other like more complicated net flow vectors as well. But also because we have a unique sink, we can say something more about our specific graph. Also, I should say because our graph is planar. Actually, I don't think it's required. Which is that vertices will not just be trees, but trees having no splits. So what do I mean by trees having no splits? Well, suppose I started drawing this graph. So this is in green here. I'm like starting to draw some graph, which is going to be a subgraph and thus a face of my polytope. But then I get to this point right here, and I've drawn this split. So it's a vertex of degree 2. Then, no matter how, because I have a unique sink, no matter how I proceed, I'm going to create a cycle because both of those edges have to end up back at the sink. So what this means is if I want to count these faces, all I have to do is count subgraphs, which basically by the number of splits they have, which gives me the dimension. So for trees, I just need to count what we're now calling in the paper as unsplittable flows. They're trees, they don't have any splits. So let's look at some motivation for how this recurrence works. Starting with, right, this is kind of a schematic version. This is the whole Pitman-Stanley graph of the Pitman-Stanley polytope. And then I just need to think about how to flow from the first, you're given A, how to flow from the first column to the second in such a way that basically I don't make any splits. I have a tree and I don't make any splits. And then I recurse. I recurse basically based on where I entered, I get a new vector J. Sorry, where I entered the second column, I get a new vector J, and I put that into my recurrence. And then count vertices of that. So then the only question remains is, which vectors J can we get from the vector A? And it's possible to just sum over all vectors, but then you have a huge sum, and there'll be lots and lots of zeros. So we wanted to find, well, what's the minimal number of these such that every term in the sum will be non-zero? To do that, we found a recurrence, but to do this, we needed this new binary relation on these integer vectors. And it's a mouthful. So it's kind of a lot. And essentially what it's saying is just kind of capturing the definition. But I'm actually going to, I couldn't just ignore it entirely, but I do want to kind of skim past it and show you kind of an example instead. I think the example says a lot more. Let's talk about kind of definition by example again. So if A and B are specifically, I'm looking at entries in 0 and 1. Vectors with entries in 0 and 1. Because, just as a side note, and we're doing that because the combinatorial equivalence class of the polytope only depends on where the vectors are non-zero. So it kind of just suffices to look at 0, 1 vectors. So we see that A, 1 dominates B if we can obtain B from A by two operations. The first operation is we can replace entries of 1 in A with entries of 0. And then we can also slide a 1 along a substring of 0. But we can't slide a block of 1. We can only slide a single. So it sounds very weird, but once you kind of start playing with it, you realize actually this is like, you feel like you've seen this before. It's like some kind of like maybe board game or something. I don't know. I definitely feel like we've seen this before, but we didn't know of any description in literature. So let me walk through an example. So here's the vector 1, 1, 0, 1, 1. If 1 dominates 0, 1, 0, 0, 1, because I can delete this 1 with the 0. I can get rid of this 1 with the 0, and I get this vector. On the other hand, this vector 1, 1, 0, 1, 1, like the same one, does not 1 dominate 0, 1, 1, 1, 1, because there's 4 1s here and 4 1s there. So the only way to get from there to there would be if I took these 2 1s and slid them both. But I can't do that, so that's disallowed. But I could slide one of them. So I could, for example, I could slide this one kind of along here. I just can't slide them both simultaneously.
So you can only make on the one slide.
Yes, exactly. I guess I should say if there were different blocks of ones, you could move multiple ones, but you can't like, so like, yeah, if there was like another one, like 0, 0, 0, you could slide this one along here and this one along here. You just can't slide two ones that are like next to each other. If that makes sense.
Make multiple lines of 1, 1, but you can't.
Yes, perfect.
Any question if you can do any number of these in a row, or just like replace one with zeros or flies?
Great question. I need to think of the flow polytope version, but I'm pretty sure it's just either or. So you mean within the vector, so long as they don't interact, I think you can do them both. Like if you can't do them in the same indice. Yeah, and if people want motivation for this later, I can show you. This is exactly what it means, basically, to flow from one column to the next in the graph. And the kind of painful disclaimer is that this is not a partial order, even though it's called, we require one domination because it's related to dominance order. And in general, in the paper, we have something that's a z for any natural number z. But yeah, so disclaimer, it's not a partial order, but it's still a very natural binary relation to consider. Yeah, and with this definition, we have everything we need to write a sum that has no zeros in it. So this is a minimal sum. The number of vertices of the Pitman-Stanley polytope is equal to the number of vertices sum over the number of vertices of the m-1st version of the Pitman-Stanley polytope, where your sum j is over these vectors that A is dominating. This chi A is just, again, this is to say I only need to look at where it's 0 and not 0. Chi A is the indicator function of A. Yeah, any questions about? Yeah, so then we say, well, why stop there? Those were 0-dimensional cases. Why not use the same argument for the whole F vector? And it works. Yeah, we get another result, it's a little bit harder to digest. There's a lot of notation, but the proof is really, really fun. And I won't unfortunately have time to show you the whole thing, but I feel like the proof, this is what like one of the problems where the proof kind of meant more than the formula, because like the intuition is really awesome, but it is a little ugly. But still, there's like, you can kind of get the rough idea, like the t-dimensional face is related to a sum over, you're changing m-1, but you're also changing the dimension of the previous spaces as well. Yeah, and while I realized I couldn't have time to show you that whole proof, I did realize I could show you the proof of kind of one of the main kind of key lemmas of one of the key lemmas of okay, so what is this lemma saying? So it's saying the d-dimensional faces, it's still a sum, but now we're defining this extra notation here. So FDNMAU. And the only thing that it's adding is that it's saying, so the D is again saying that the graph, this is the number of graphs having a certain Betty number, corresponding to a certain dimension face. But now the U is saying that the support along the mth column is going to correspond to some vector U. So let me explain. And so then we're taking a sum over a product of these things. Let me show you the illustration, which I think is kind of fun. So this is the same argument I showed you before, where you start drawing a graph, you realize that any split must correspond to a cycle. But more than that is true, because our graph is planar, this is where we need planar, every cycle corresponds to a split as well. So splits are in one-to-one correspondence. Sorry, splits are in one-to-one to correspondence with cycles that are contributing to the Betty number. So what I can do is I can fix some column C and add, like basically for some, like I want to find the number of faces having basically support across these, right, support equal to U across these columns, the edges of these columns. And then what I can do is I can count I splits on the left on one side and D minus I splits on the other. And the number of those two ways, I just have to multiply them together. and then sum over all possibilities of I, and sum over all possibilities of U. And that's exactly, going back, what the theorem is about, or what. Yeah, so it's just the proof by picture of why that works. And then this was I could not include this just because I thought this was really cool. It's just a picture from the proof of an example of the proof of the more general theorem, explaining why the binomial coefficients come into play. And the rough idea is that you get in the same way that the regular Pitman-Stanley polytope breaks up into a product of simplicity. That original argument basically goes by looking at the kind of block structure, where blocks are coming from basically where there's non-zero entries in your vector. I can say more about that after the talk if people are interested, but the rough idea is you use the same blocks as the proof that the regular Pitman-Stanley polytope is a product of simplicity. And then the binomial coefficient is coming from the fact that you're choosing a certain number of edges to connect those blocks. So there's 2 blocks and you're choosing 0 edges. There's 2 blocks and you're choosing 1 edge, or you choose both edges to kind of connect them.
Like, how do I see the edge that you're choosing? I'm not
Oh,
quite.
that's just because it's too dull. There's a green, I'm adding like these green edges
Oh,
right
okay,
here.
okay.
Yeah, so yeah, sorry about that. Yeah, I wish I could really. No, I can't.
No, it's okay. I see the green now.
Oh, okay. And the colors are just representing the cycles that are being formed by. Yeah. Now it's frozen. All right. And so then we go on to the next thing. So that was recurrences on vertices and faces. But we were also able to start computing generating functions. But the idea here is we use the transfer matrix method, which I will kind of define in the process of doing this if you haven't seen it before. Or if you have, you already know what it is to come. So we look at dn, which is going to be a brand new graph. Like at first, it seems completely unrelated to anything we talked about, but you'll see it is connected. And it's defined as follows. So it's a graph where the vertex set consists of all vectors in 0, 1, of length n. And then there's an edge from a vertex of one vector, j, to another, k, if j1 dominates k. It turns out we're able to count the vertices of this generalized Pitman-Stanley polytope as paths of length m along the edges of dn. So n is coming from the dn, m is coming from the length of it. So let me give an example of this. So here I have my graph D3 on the left. And on the right, I have my grid. So I mentioned before, and we're trying to count vertices. So I mentioned before that vertex corresponds to some tree in the right graph, which is not having any splits. So I need to show you how this graph on the right corresponds to a path of length m, in this case 6, in the graph on the left. Sorry about that. All right, so how does that work? The idea is we're going to look at, once again, the support along each of the columns of edges. So first off, I'm starting with vector 1, 1, 1. So I'm going to start by looking, the beginning point of my path is going to be vertex corresponding to 1, 1, 1. And then the direction we take, or the edge we take in the path is determined by the support along these columns. Or these, yeah, in this column along these edges. So the support is 1, 1, 1. So I'm going to take the path that goes from 1, 1, 1 to itself. And then the second column is again support 1, 1, 1. And so I take that same path, that same edge again. And then I have 1, 0, 1. So I go along that edge, 1, 0, 1. then 0, 1, 1, then 0, 1, 1 again, and then to 0. It's a path of length 6, and this is how it corresponds to this this tree on the right. And the reason that's important is because then the transfer matrix method, which we're just citing on C1 of Stanley, basically just automatically gives this result. So it says that the generating function, and it's a lot to digest, excuse me, to digest, but the rough idea of the generating function over M of our vertices is equal to a rational function where the numerator is a sum over determinant of our adjacency matrix. And the denominator is just this nice simple thing. And these adjacency matrices are growing at the order of 2 to the n. So like in practice, this could solve, like we could say this is a solution to, it gives a generating function, but like we can only calculate the first 6 or 7 before it's really like not even feasible. But it does give one result that holds for all generating functions, which is that the generating functions will be a polynomial in M of degree n was 2 to the n minus 1. And that's coming from the fact that this this denominator is of the form 1 minus x times 2 to 2n. Yeah, because like that, if rational function is of that form, then this factor will just be a polynomial in M of degree 2 to the n minus. Yeah, so we thought that was cool, and we tried some other things. So we have some other results, which my collaborators were saying, be sure to mention. We have a flow characterization, which you kind of described a little bit in terms of unsplittable flows. We have a more general thing for B, non-zero. I told you that lattice points correspond to plane partition. And since our polytopes are integral, that means that there should be, the vertices should correspond to some special plane partition. And we described these. We also have a proof that these two quantities as functions in M expand as non-negative polynomials in the polynomial basis of n plus 1 choose k plus 1. Yeah, and I won't have time to explain all of these, but I want to let you know. Okay. So I think, do I only talk till 50? Okay, so I'll finish up in just a minute. Switching gears a little bit, so that all of that will be on the archive in probably a week or less. Just about done. That's a collaboration with those that group I mentioned. This is something that Alejandro has me working on kind of on my own. This will be part of my dissertation probably. It might not come out until later. So it's work on the face lattice of these polygons. So there's two results in this direction so far. The first is that the face lattice of the generalized Pitman-Stanley polytope at J is a poset quotient of the one valued at 1. And I wanted to share this because I thought there's some cool illustrations again. So we define this map theta J, suppressing the n and m, which are secretly there. And it's defined as follows. So basically you look at a graph corresponding to a face in this Pitman-Stanley polytope, the face lattice of the Pitman-Stanley polytope at all 1. And then you look at basically edges, like you take your net flow vector, you replace it with whichever j you're working with. In this case, it's 1, 0, 0, 1, 1. And you look at all the vertices all the edges that you can still keep that are basically, downstream of some node, like some vertex in your support. So, for example, this 1 gets replaced with a 0, but we get to keep these edges because they can still be kind of fed by this 1 that's up here. Whereas as soon as we replace this 1 with a 0, all of these edges in red, there's no way to kind of fill in for that missing 1, and so they just have to be deleted. So it's kind of like the canonical map you can make from one of the face lattices to the other. And we define an equivalence relation on basically just by the fibers of this map. But the crazy thing I should maybe say here, the reason this is not really, this was difficult and kind of not trivial, is that this map, so then, yeah, the result is that, the lattice of PSNMJ is isomorphic to the lattice of PSNM1 mod equivalent. But this equivalence is actually not a lattice figure, which is the kind of crazy thing. We actually, the poset quotient, which leads to isomorphism. That was actually very, very hard to prove. Yeah, well, maybe not very hard. I shouldn't overemphasize. It was a little bit confusing at first because we were like, oh, I thought it was going to be a lattice.
Did you say J is 0, 1? Did
What's that?
you say J is a 0, 1 vector or J is arbitrary?
Oh, yes, J is a 0, 1 vector.
So this is just you take PSMN1,
Mhm.
and then you're doing a facet deformation, you're just pulling some of the facets in to 0 instead of 1, right?
Yeah, I think so. Yeah. Yeah, and so the second result is I'm going to kind of lead up with some intuition first, and it's not fully proved yet, and actually I'm hoping for some feedback from this audience. So I gave you this recurrence on the F vectors from before, and in the case that A is all 1, like the setting we're working right now, it becomes simpler. And these binomial coefficients, they're simply counted by the number of 1s appearing in J. Choose K, where you're summing over K. And if we look at this closely, we realize that, well, here's a sum over some kind of 2 to the n number of elements. And then we have a binomial coefficient. We were looking at these kind of computationally, we're like, hey, these look like they should be related to the structure of an hypercube, an n cube, where, because this is the F vector of the n cube. We thought that there could be some connection. And the connection we came up with is as follows. So it's the same conjecture. I think we just about have a proof. Maybe it hasn't been fully written up. But this is how it works. So we're saying that the Pitman-Stanley polytope, NM valued at all 1s, isomorphic to a certain thing. So what is that? So the n cube has a description where you can write all of the nodes in terms of words in 0, 1, and star, which was originally going to give an example, but I suppressed it for the sake of time. But the idea is you take each of those nodes and you replace it with an m minus first, the face lattice of an m minus 1 Pitman-Stanley polytope, essentially evaluated at that vertex. What I mean by it is you replace the stars with 1s, and then you have a 0, 1 vector, which you can then put into your Pitman-Stanley polytope argument. And so my question is, like, we didn't know what kind of structure this was, and we weren't sure if you had ideas. So we think of it as like a Cartesian product, but one factor is kind of changing based on the other factor. And the way we were able to represent it formally is by, again, doing like a poset quotient. But it feels like there's a better way to describe it than that. Yeah, so I'm curious if people have thoughts. Maybe let me show you an example, which is not going to appear well in the slides. I apologize. But let me just kind of zoom in. Or maybe afterward, I'll invite people to just come up and get very close, and then you can see.
If you leave these slideshow,
What's that?
if you leave the slideshow view, zoom in on the slide visually.
Oh yeah, sure. I'll do that. But so here's the 2 cube, the face lattice of the 2 cube. And basically every one of these nodes is being replaced with an entire face lattice of a minus first Pitman-Stanley polytope. Or for example, this node is 0, 1. So it's being replaced with the 0 Pitman-Stanley polytope at 0, 1, 0, 1, and so on. So like here we're getting 4, that's why it's so messy. Yeah, I'll try to zoom in afterwards to show people. No, no, not. Oh, all right. Don't know why it keeps reading, but okay. Yeah, so I'm out of time. Final remarks. So what have we done? We have some partial results on the face lattice. Other things I haven't been able to talk about, we're working towards non-recursive formulas for faces. Volume results later. Teaser on volume results. So recall that the normalized volume of the original Pitman-Stanley polytope at all 1 is related to parking functions and +1 to -1. They also proved in the original paper this product formula related to standard Young tableau. So the normalized volume of the mth version is a product of standard Young tableau of a certain shape times this. And they asked for a combinatorial proof. And we've been working on it, and we have the case done for n = 2, and also some bijection between this, like, there's this Linsky formula that kind of do subdivisions. We have a bijection between standard Young tableau of the shape and pieces. But that's to come later. So open problems. The original Pitman-Stanley polytope was the whole thing was motivated by probability. And we believe that there is some relevance for probability here, but we don't know what it is. And also open problem, but something that that I'm also interested in. So if you start, definitely feel free to try it, and then, but like, let me know if you work on it, because I want to be impressed. Is, to find a closed formula for the vertices, number of vertices and faces. And selected references. Thank you so much. It's been such a pleasure.
Any questions for William?
There's some canonical, like I know if you take the -1, 0, 1 net flow, then you have decay triangulation. Is there a canonical triangulation for the other net flow vectors? I've really only thought about the -1 case.
Yeah.
Or a canonical subdivision, like if you take these, or in your particular case, I was just trying to think, like, if you have routes, the vertices corresponding to routes and -1 net flow. But you're saying that if you have other net flows in particular cases, you get like funding of trees and some notion of like compatibility for trees. I was just curious if I think.
Yeah, I feel like Professor Yokai knows more. I know that I know there's this I guess when I think of subdivisions and flow polytopes, the Linsky formulas comes, like, I just know there's that, and then yeah, but I'm not sure.
But that's not the Linsky formula is coming from a constant. Constant term identity, right? So you like lose the combinatorics.
Well, you have
Or maybe
combinatorics,
like in general, you get it in special cases. I'm remembering parts.
well, I think there's some combinatorics in this insofar as you have these conditions on tuple vectors which you can interpret as paths. But you're right. I guess I see what you're saying, but not really the same combinatorics that we were talking about here. Yeah, I'm not sure. That's right.
In general, for general net flow, I think their subdivision of it will work for more general net flow. That's just based on her plane.
Yeah, just that example.
For the base lattice for the generalized Pitman-Stanley polytope, when m is 1, like are those results? Were there existing results for m = 1 for the base lattice?
Oh yes, precisely. So for m = 1, for m = 1 and b = 0. Because I don't think anyone looked at b equals anything else, but me, because somehow that wasn't looked at. But for m = 1, it's combinatorial. The phase lattice is a product of simplicity. And so In fact, the other reason I kind of said that the reason we haven't quite finished with this conjecture is because when we realized that it's like a hypercube, when you do its replacement, we're like, wait, we're only working in the all ones case. So it makes you think maybe there's something similar where instead of the hypercube, it's the same product of simplices, and then you do this replacement procedure. So we were like, well, we might as well just work on the general case. Maybe now let me try to zoom in. You can see, and these are, so I actually, only zooms in that far, no. Well, these you can, if you come up to the board, you can see though, they're all like actually drawn out as the faces of these graphs. But so for example, like these two right here are corresponding to these two.
So that's like the base lattice of triangle without the empty set.
Oh, yes, sorry, I
Okay.
meant to say, I think should have said, exactly. So I have to remove them first.
Okay. Okay, going from right to left, I see then an edge, a triangle, a square. And then it's squared again, but then all these groups are 4, 4, 5, 4, 1. This column.
Oh,
Oh, that's a square.
Mhm.
Okay, what's the next one?
so you're saying here?
Yeah, that looks like a square.
So
Yeah.
this is a square. I just had to put them around. Yeah, so sorry.
okay.
This is the
Okay.
top face of this one.
Put the square there and then another square on top.
Yes. Oh, yes.
Oh.
Because these are the m equal 1. So this is the face lattice. I hope it's said. This is the face lattice for m equals 2. And so we do m. Oh, sorry. We do m minus 1. So these are the regular ones. So yeah, each of these is a product of simplices. So in the case
Yeah.
this is the 2 simplex. Because the vector is only 1, 1, we only ever get simplices. But if it was longer, these would each be products.
Okay. No, when you said that big blob there, I couldn't see that was a square on top of the
Yeah,
square.
sorry. Because
Okay.
yeah, that wanted the faces to be in the same.
Yeah.
The same one. Great question.
Let's think the lane again. No, I'm
You're
here.
gonna-
Yeah,
Okay, I got it.
yeah. Gotta catch a plane.
Hi, I'm Ben Braun. Nice
Oh,
to meet you.
nice to meet you.
So, anyway, it was great talking. So right now it's so, but didn't work.
Yeah, that's wish I had more time to.
Yeah, no, but
so
anyway,
there's
this is a really interesting talk and